All right, let's just review quickly where we are and where we're going. You do have your test on chapter. I know a couple people have turned in the first test. Oh, here comes Houston. That's good to see. So let me get him marked here if it'll admit him. There it was. Didn't want to admit him at first, it seemed like. Okay, top part of the alphabet doing pretty well, 3 out of 4. The bottom part of the alphabet completely vacant here. So hopefully they'll be coming in. All right, Houston, I was just asking, I'd ask if there are any issues, concerns, problems, anything else. Do you have any before I start into my tirade?
No, sir.
Okay. Um, well, where we are, you've had test 1. A few people have turned that in. Others hopefully still working on it. We then moved, and that was chapter, let me get my memory right. I believe it was chapter 8, wasn't it? Yeah. And then we went to chapter 9. We did 2 sections in 9, 9.1 and 9.2. And then we're in chapter 10 now. We didn't do 10.1, but we're doing 10.2, 10.3, and today we're starting on 10.4, which meant in about few minutes that I had in between class. Oh, here comes James. So the bottom part of the alphabet is going to get some representation now. Okay. So James is here. So we've got half the class here. Hopefully the others will be coming in soon. James, any questions, issues, concerns before I get going on my spiel?
Were you able to get my 3 emails and my test? I had turned one in on Blackboard, so I was gonna try to turn the other ones in if you didn't see the email, but I couldn't find the place to put it.
Okay. Um, all right. Well, when did you turn in the one on Blackboard?
I turned it in like about I think 2 or 3 days ago.
Okay. Well, if it's over the weekend, I was completely cut off from any internet at all. Had gone to the farm over in Georgia, and we're way out in the country, so we don't have good internet to begin with. It's all through a DSL, and we got there on a Friday, and Friday afternoon, evening sometime, the internet went out, the phones went out, everything was out, not just ours, but everyone we knew around us were the same things. And then that didn't come back until Sunday evening sometime, and of course we left Monday morning. So I was completely cut off from internet for most of the weekend. So if it was any time during that time, and I've been trying to catch up since then, and you know, we drove back in the morning on Monday, so I lost my 2 hours of office hours then. I got some things caught up on Monday evening, and then yesterday I was in class all day long, and this morning I got a few things caught up, but basically I'm running way behind. So I probably have it just and I probably won't have much of an opportunity to check on it until Friday morning. But Friday, I think, well, it seems like everything's happening this week. We're having some problem. We're in an old house, 1930 house, and periodically it has problems, and some of which have typically been plumbing problems, and we're experiencing one of those right now. So the plumber or Roto-Rooter or somebody is coming on Friday. So part of my day on Friday will be taken with that. But once that gets over with, I'm going to try to work on things this weekend and to get caught up as much as possible. So don't sweat it just because you haven't seen it yet. Like I saw Kyle sent his test in quite a while back, and I could see him as I was working down the emails. I could see his name. I was getting closer and closer. Then something come up. I'd have to take off and do something else. Then a bunch more get there, work down, and I still haven't printed yours off yet, Cal. So I know you were probably one of the first ones to turn it in. I still haven't printed it off yet. So, but once I do, I've got the key made up and ready to go. I just haven't had a chance to get it done. So I'll try to get that soon as I can. But glad you alerted me to it. If I can't find it somewhere, then I'll let you know, and you can. And it sounded like part of your question was this: where do you do it? Now you have three possibilities of where. How is another issue, but where you can. I think I put a thing out there called Test 1 in one of the weeks. And because that's such a pain in the neck to go through and find out which week that was in, you can also do it through message, Blackboard messages, or you can just send me an email and attach it to an email. I think that's what Kyle did, was attach it to an email. That's perfectly fine. A message is fine. Attach it to a message, or load it directly into that place. I can't remember which week it was, week 5, week 4, sometime in there. They have a place for test 1. And as I was starting to say, before some people started coming in, more people started coming in, I started working this morning on your second test. That's 9-1, 9-2, 10-2, 10-3, and 10-4. I've got made up the test, but the package that the test bank does it in Word format, but they have it in such a convoluted Word format, you can't extricate and do any adjustments to it. It just screws up everything. So I have to retype it all. So I'm in the process of retyping it now. I've got it about halfway done, retyped. So, and again, this afternoon, we're losing about half of our, I'm losing time this afternoon because my wife's, I can't even remember what year my wife's car is. It's maybe a 2010 or something about like that. And it's beginning to give enough problems that she's not confident driving it anywhere but in town. And she's going to have to go. Unfortunately, with COVID, we haven't been going anywhere, but we're going to have to make some trips that she'll need her car. So we're getting her a new car this afternoon. So as soon as I get out of my third class this afternoon, we're heading up to Jasper. That's the dealership. We got the best deal on the car that we wanted, and so we're going to be doing that. So there goes my 2 hours of office hours this afternoon. So it seems like I can't win for losing. And then tomorrow I'm in class all day long, and then finally on Friday, after Roto-Rooter leaves or whoever it is that comes in, after that I'll have time to try to work on things. But who knows? I may have a honey-do list by then, so there's always something. But I'm going to try to get caught up, hopefully this weekend. Sorry, yeah. So what I was saying is I'm in the process of making up your next test, so it's a good idea if you haven't got that first test in to get it into me, okay? The second issue with that is, and it's not really an issue with that, but please be working on your research papers if you haven't already done that, because I think I've got only one in from this class there. I'm not sure I've got it. No, I've got 2 in, one graded and one not graded, but I'll try to get those caught up too. And some others may have been sent, but I haven't printed those yet. So I'm going to try to catch up. Y'all work on catching up too. We're rapidly approaching midterm. Next week is week 8, which is halfway through the term. So let's make sure we're moving on all the things we need to. All right, any questions, issues, concerns from there? All right, just a quick review now. 9-1 sequences, 9-2 series. 10-2 is the beginning of parametric equations, okay? And 10-3 was parametric equations in calculus, okay? 10-4, now we sort of go to a new area. Now we didn't do the conics part here of chapter 10, that was 10-1. Parametric equations, that was 10-2 and 10-3. Now we're moving to polar coordinates, that's 10-4. Good buddy. Okay. Now I can't get it to advance until I click on the screen. There we go. So 10.4 is polar coordinates and polar graphs. Okay. Objectives here, understand the polar coordinate system. Okay. That's kind of a nebulous, I don't like those kind of objectives because how can you measure understanding? That's sort of another issue. But these are just blah, blah, blah stuff. Anyway, next, rewrite rectangular coordinates and equations into polar form and vice versa, polar form into rectangular. And you'll see that's a pretty simple process. I'm almost guessing that you've had this before sometime in your way distant past. Okay? Then we'll sketch the graph of an equation given in polar form. We'll probably do more than one. Okay? And we'll find the slope of a tangent line to a polar graph. And that may turn out easier than you might think. And then we'll identify several types of special polar graphs, and that's pretty much will wrap up 10-4. Good buddy. Okay. So let's start with polar coordinates. What are they? How do we use them? Why do we use them? What are their advantages, disadvantages, that type of thing. So far, you've been representing graphs as collections of points x, y, ordered pairs on the rectangular coordinate system. Okay, also called the Cartesian coordinate system. Rectangular because you have x's and you have y's. Those two dimensions give you rectangles. Okay. Cartesian coordinate system just because it's named after Rene Descartes, who came up with the XY concept. Now, the corresponding equations for those graphs have been either in rectangular form, which is what we have been doing up before 2 sections ago, or as we did in 2 sections ago, start doing things in parametric form. So either your function y is a function of x, or x is a function of y. That's the rectangular form. Or x is some function of t, and y is some function of t, or some other parameter, and that's parametric form. In this section, we'll study a coordinate system called the polar coordinate system. To form the polar coordinate system in a plane, you have to have an origin, a fixed point O. Okay, that's called sometimes the pole. That's where they get the name polar coordinates, but quite often we call it the origin, sort of to have a touch point, because we call the crossing of the xy plane the origin in rectangular. We can call this point the origin in polar coordinates, and basically kind of superimpose them on each other. Okay, but more correctly, I guess it would be called the pole rather than the origin, but either one. Construct from that point O, that one fixed point O, an initial ray called the polar axis. Now, you probably have already used to having the positive x-axis as being back in trig. That's where you usually measured in standard form your angles. So we're kind of used to that. Guess what? That's going to be our polar axis most of the time when we're dealing with polar coordinates. What would be the positive x-axis, starting from the origin, the pole, and going to the right in a horizontal fashion. Okay, now from there you do another ray or axis that goes up to some point, usually not on that axis, like this point P. Okay, now when you get to this point P, it has two coordinates, not x and y, how far you are vertically, horizontally, and vertically from the origin, but two coordinates r and theta. Now r is a dimension quantity in distance. Okay, theta, however, is not a dimension quantity in distance. It's a angular measurement. Okay, so from this polar axis, again going in a counterclockwise direction, the amount that you go, just like you did in trig, that direction, theta, is going to be your second coordinate. How far you are angular-wise from that polar axis. Okay, what is the r then? The first of those coordinates? That's your distance from the origin. So you have one distance measurement directly from the origin to the point. That's your r, and then the angle that you make from the polar axis, which is a positive horizontal axis, up to that point or down to that point or wherever, that's your theta. So those are your two coordinate values. R, distance from the origin, theta, the angular distance from your polar axis. Those are your two coordinates. From then each point P in the plane, wherever you are in the plane, can be assigned a set of polar coordinates. R is the distance from the origin, the O to P, and theta is the directed angle counterclockwise from the polar axis to the segment OP. Now, I happen to say ray, which was incorrect. It's no longer a ray. Back in trig, we called it a ray. This is called the line segment because it has a fixed length r. It doesn't go on indefinitely. So this is, the polar axis is a ray with a one fixed point, and the other goes indefinitely as far as you need it to go. The what we used to call the terminal side of an angle, that is a segment. It has a fixed length from O to P, and that length is R. Okay. Now, you can almost imagine, I hope, imposing rectangular coordinates on here and how they relate to these two. But we'll see those, okay, later. Give us a few minutes with this first. This figure here, 1036, shows 3 points on the polar coordinate system, okay? Now, you don't have an XY grid anymore that you did in Cartesian coordinates. What you have is basically a circular grid. You have a radius of radius 1, a circle of radius 2, a circle of radius 3, and as far out as you need to go. Concentric circles about that pole or that origin, okay? That gives you approximately your R. So anything on the circle of radius 2 is going to have an R of 2. Anything on 1 would be an R of 1. Anything on 3 would have an R of 3. Okay? Whatever your angle might be. Now anything in between, 0.5 would be right in there. 1.5 would be there. 1.25 might be there. Pi might be right out here somewhere, just a little beyond 3. So any point, any real number you can represent here as the R, you just don't have a circle to put it on. Well, guess what? In a rectangular system, you don't have a line for 3.748 either. You have to estimate. So your R is which circle you're on. Your angle, this one here, happens to be, appears to be, and they say is pi thirds. So what would that point right there be? Coordinates 2, because it's on circle 2, pi thirds, because that's how far it is from the polar axis up to that point. Now, here's where you get into some issues. There's always issues. If you're out here on circle 3, then your R is 3, but now you're down here below the polar axis. And if it happens to be an angle of minus pi 6 down here, then there you could express it this way: 3 comma negative pi 6, because you've gone clockwise from here, just like we did in trig. But just like we did in trig, you have coterminal angles. Remember when we talked about that? Same terminal side. You could have called this 3, and then you would have done half a pi, a whole pi, 3/2 of a pi, and then another 2/3 of a pi. No, I'm sorry. Yeah, 2/3 of a pi, because you just have, no, that's not right either. 1/3 of a pi. I'm sorry, 1/3 of a pi. 1/3 of a pi more. So that would have been 3/2 pi plus 1/3 pi would be, oh goodness, 11/6 pi. Okay, so this point could have also been 3 comma 11/6 pi. Same point there. Okay, this shows one difference between polar coordinates and rectangular coordinates. Once you have a point in rectangular coordinates, given the signs and everything else, one set of ordered pairs uniquely defines that point. We've just seen here, this could be, and here it is right here, 3 comma minus 11/6 pi is that same point here that we were using 3 comma negative pi sixths. Okay, same point. And guess what? You can keep going around and around 2n pi this way or negative 2n pi this way and have an infinite number of coordinates that represent that same point. And we'll see a little later, if we had drawn our ray up here in this direction, but then called it a -3, that would put us right back to that same point too. That would have been 5/6 pi would have been the theta part, -3 would be this. So, oh my goodness, it's just gotten more confusing. Polar coordinates in my mind can be a bit more confusing, but on the other hand, they have some circumstances where they really simplify matters big time. Anything that has circular symmetry, far better to use polar coordinates than rectilinear components. Okay, so let's move on. Notice that in this system, it is convenient to locate points with respect to a grid of concentric circles, that's what I was just saying, intersected by radial lines that go through the poles, and that's how you do it. With rectangular coordinates, each point xy has a unique representation, that's what I was just saying, that is not true for polar coordinates. For example, let's just pick your r theta wherever you are, any r theta. Then, guess what? R comma 2 pi plus theta gets you right back to that same point again. You go theta off the polar axis, and then you know another 2 pi gets you right to the same place. Another 2 pi gets you the same place. Another 2 pi gets you, or a minus 2 pi gets you the same place, or another minus 2 pi. So actually, it's r comma theta plus 2n pi, where n can be any integer. Those are all the same points. Now, and we saw that in B and C of that last thing. But also, because r is a directed distance, the coordinates r theta would also be the same as minus r and then theta plus pi, or theta minus pi. You go halfway around the circle. Do a negative r, but go halfway around the circle, you're back at that same point again. So not only do you have an infinite number of representations with theta, you with just 2n pi, you have plus or minus r with theta plus n pi. Well, no. Well, odd number of pi's. Let's put it that way. So, not quite as simple in many ways as rectangular coordinates. Sometimes called rectilinear. Sometimes we'll slide that in. In general, the point r theta can be written as, and here's what I was saying, r comma theta plus 2n pi. That same theta here, but then add any multiple of 2 pi to it, where that multiple would be a positive multiple or a negative multiple, as long as n is an integer, not fraction, not decimal, integer values, positive or negative integer. Or r theta could be minus r, and then theta plus your pi, or 2n plus 1 pi. Okay, so that's the other way of expressing it in a single expression, 2n plus 1 pi, where n is any integer whatsoever, positive or negative. Integer though. Moreover, the pole is represented by 0 theta, where theta could be any angle whatsoever, whereas in a rectangular coordinate system, it's 0, 0, and that's the only representation for it. But here it could be 0 pi halves, pi tenths, pi thirds, whatever, okay? Because if you have no radius, you're there at the origin. So any angle whatsoever. Okay, so there are a few issues with polar coordinates that you don't have with rectilinear or rectangular coordinates. Okay, now let me make sure that we haven't skipped anything. No, we're now on page 720, coordinate conversion. How do we get back and forth one to another? To establish the relationship between polar and rectangular coordinates, let the polar axis coincide with the positive x-axis. Hey, that's what we said before. And the pole with the origin. Yes, that's what we said before. That's why you call it either O or origin or pole, okay? As shown here, okay? Now, they haven't shown the circles around here, but if you had put the circles on here, that would be the polar coordinates. This is just showing rectilinear coordinates or rectangular coordinates. Okay, because xy lives on a circle of radius r, whatever x you have, whatever y you are, have x squared plus y squared is equal to some r squared. Whatever that r is, that is your polar coordinate. So guess what? You just got your first conversions. Okay, r squared is equal to x squared plus y squared. So if you have an xy point, any xy point in the world, you know your r for that one. It's x squared plus y squared is r squared, so the r would be the square root of that. Now, here's the other thing. Now, I can't remember. I think most of you, but I don't know if all of you have had physics yet. Have you? Any of you not had physics? Okay, it sounds like you all have. I know James has, Kira has, I'm pretty sure Houston has. I just wasn't too sure about Kyle. You've had physics too, right? Don't know if I still got them here. Okay. All right. But from physics, here are some things. From this same graph here that shows you x squared plus y squared is equal to r squared, so that's how you can get your r. You can also gather that your y is r times the sine of theta. Oh yeah. So now if you know your r theta, you know immediately what y is, and you know immediately what x is, because x is r cosine theta. So there's how you go back and forth. So you're, goodness, my nose is itching. Now if all you know is r theta, xy, you also know what theta is, because x over y over x is the tangent of theta. So if you know x and y, put y over x and you get tangent theta. How do you get theta? Take the inverse tangent of it. So here are your three trig identities, you might say, or representations of this. Tangent is always x over y, cosine is always x over r, sine is always y over r. This one you use to go from xy to r theta. You use this one to go xy to r theta. This gives you your r, this gives you your theta. This one, if you multiply both sides by r, then you have r theta on this side, so you can go from r theta to x, and this one you'll have r theta to y if you multiply by r. So those are your four basic equations that some combination of these equations will give you all the convergence that you need. That's how we convert. Now, we've been dealing as if r is positive, but those same relationships hold when r is negative. Now in trig, we never let the r be negative. Okay, that's the difference here. So get used to that. In polar coordinates, r can be negative. In trig, remember we said the hypotenuse is always positive, the r is always positive. We always kept emphasizing that. Now r can be negative as well. So here's theorem 1010, coordinate conversions. The polar coordinate r theta of a point are related to the rectangular coordinates xy is this. If you know the polar r theta and you want to get the xy, simple matter, x is r times the cosine of theta, y is r times the sine of theta. That's it. That's it. Okay? But if you know the rectangular coordinate system, xy, if you know that point in xy, you can get to r theta by doing the tangent of theta is y over x. That's your basic definition of a tangent, which I would have taken one more step and say theta is equal to the inverse tangent of y over x. Now there are some issues with that as well, because you remember inverse tangent has a limited domain. Minus pi halves to pi, well, let's see. Yeah, that's not quite said right. It's only defined for minus pi halves to pi halves. Okay. Now, r squared is x squared plus y squared. We already said that. I would have taken this another step and said r is equal to square root of r x squared plus y squared. But you have to remember it could be either be plus or minus. And depending on which sign you take for r, that will determine which theta you use from your calculation of theta. So there are some issues there, okay, but they're pretty easy to work out if you just think through them. These work perfectly every time. These you might have to do a little bit of manipulation, but it's not too much. Okay, so here's example 1, kind of the middle of page 720. For the point r theta is equal to 2 comma pi, I don't like that they're doing all the work for you, so let's just go to the whiteboard. We've still got 5 people here, so, I mean, me and 4 students, so keep wondering where the others are. Now, before we do anything, I want to move, whoa, that was completely bizarre. Okay, gonna move this over here. You can't see it, but that's moving my taskbar toolbar out of the way. And then I'm going to clear that scratch I did on the board. And then I'm going to scoot my whiteboard over so I have the maximum amount of white space on which to write. Okay, that's about the best I can do. Okay. Let's do example 1. Here's a point. They're giving us r theta. Those are 2 coordinates in polar coordinates, and they give us that to be 2 comma pi. Okay. Now they're asking for what are your xy coordinates. Okay. Remember, these are the simple ones, these are exact ones. X is always r times the cosine of theta, and y is always r times the sine of theta. If we know r theta, we know x, okay? And that x would be uh, 2 times the cosine of pi. Y would be, excuse me, 2 times the sine of pi. Okay. I'm going to have to take just a moment and get me a swig of something because my head is closing up on me. hope it's the change of weather allergy type thing, but those are famous last words, aren't they, Cal? Okay, so let's see if we can calculate. Oh, there it goes. Well, what's cosine of pi? Cosine starts at 1. At pi halves, it goes down to 0. At pi, it's at -1. So if cosine pi is -1, 2 times that would be -2. Okay? Y, sine starts at 0. At pi halves, it goes to 1. At pi, it goes to 0 again. So the y would equal x is -2, y is equal to 0. So the xy coordinates corresponding to that r theta will be simply -2, 0. Now, if you think about that, that makes perfect sense, because r 2 theta and coordinate, okay, you start on the x positive x-axis and go, I'm not sure, I'm looking at my reflection in this the picture here, and I'm not sure which way right and left are for you, okay, but if you start here and go 2 units out, and at 0 degrees you're on that axis, and pi takes you to the opposite side, you're on x equal -2, y is equal to 0, because you're still on the x-axis, you're just on the pi side. You go pi units across, okay? So there's the point. Let's see, do they have a B here? I think so. Here's another point. R theta is equal to √3 pi sixth. Okay. Now, again, to get rectangular coordinates, really easy process. You just plug it in. X is equal to the square root of 3, that's your r, times the cosine of pi 6. Well, cosine of pi 6 is √3 over 2. So that would give you 3/2. √3 times √3 is 3. Okay, so there's your x. Your y is equal to square root of 3 times the sine of pi 6, which would be the r is √3, and sine of pi 6 is 1/2, so it's √3 over 2. So your xy coordinate, let me write it over here, the xy coordinate would then be simply 3/2 √3 over 2. Okay. Yeah. Okay. Now, okay. That's how we did it. Let's go back and see how they did it. Basically, I'm pretty sure it's got to be about the same way. I can't think of many other ways to do it. Still have 4 students here. Make sure nobody's in the waiting room. No, they're not. Excuse me. Well, come on. Here we go. Go back to our PowerPoint. 10.4. Good buddy. Back to current slide. Okay. So there's where we left off. X is equal to r cosine theta, which is 2 times cosine theta, cosine of pi. Cosine of pi is minus 1, so that would be 2 times minus 1 is minus 2. Y is r sine theta. R is 2 theta pi, so 2 times sine of pi, but sine of pi is 0. So you've got your xy coordinates. Rectangular coordinates are negative 2, 1, not negative 2, 0, which is exactly what you would expect, I hope. Okay, the next one's, for some reason it elevated up here. Now, I can't remember if it was this class or the next class. I think it was the next class. I put a test out there, and I was using a fairly new Word version because that's what they sent me on the computer. I would have been happy with the older version, but they sent, this is the college computer, and they had probably the most current up-to-date Word version out there. And when I did the test in that, then some people couldn't read the test. There'd be blanks where I put, say, an equation in. Well, that's because Word, Microsoft, had gotten really fancy with it and had put in a new kind of equation editor, not like the old one that was very easy to use. This one you had to write on the screen and then keep writing until it could guess what you were trying to write, and it's a real pain in the neck, and that's why it takes me so long to make out a test. But that's where we were, and no, I think it was this class, now that I think about it, that you couldn't read all the questions on the test. But I know it happened in another class too, in pre-calculus algebra class. Same thing happened there too. Anytime I use equation editor. And you can see, and the reason I brought this up, right here is the same deal. This was typed in, and this was done with an equation editor. And notice the equation editor jumped up there. These are jumped up here and here, whereas the typewritten part is down here. I'm pretty sure that probably in the original, whoever was doing this, it looked fine. But then when they went through Blackboard or PowerPoint or whatever, it screwed them up. Okay? And PowerPoint is notorious for doing that. When they go to a new version, they kind of don't give a hoot whether you can use that on your old PowerPoint. They want to sell you new software. So they, I think, sometimes almost intentionally make things so they're non-compatible, forcing people to have to buy another product of theirs. So they get more money. So I'm not a big fan of Microsoft. I've used WordPerfect for much of my word processing life, and it almost seems like, except for some really rare thing when they went, say, from function keys to basically keyboard type stuff, except for very rare occasions, they always made sure the current version was comparable and compatible with the previous version. So people could keep using the same one they had, and when they wanted the newer features, then they could buy the new version. They didn't force them to. And that's, I think, what's happening here. If that looks bizarre, that is bizarre, and it's probably a combination of PowerPoint, and you see, PowerPoint is a is a Microsoft product as well, and not even their packages, Word and PowerPoint, communicate each other well. It's shoddy technology in my mind. Okay. But here's what you get when you put r theta is root 3 pi 6, x is equal to root 3 times the cosine of pi 6. Well, cosine of pi 6 is root 3 over 2. Root 3 times root 3 is 3 over 2. Y is root 3, your R, times the sine of pi 6. Well, sine of pi 6 is 1/2, so root 3 times 1/2 is root 3 over 2. Okay, so those are your, so here it is again. This is almost laughable, okay? This is supposed to read, so the polar coordinates are x, y is equal to, but because they're not compatible, it typed those in up here and covered your words here. The xy coordinate pair corresponding to this coordinate pair and polar coordinates would be 3/2 root 3 over 2. Okay? Laughable. Okay. Here was the graphic that I was doing. On the first point, 2 pi, get on this concentric circle 2, radius 2. That would be the circle that went something like that. Okay. And when they put this in there, it blocks some of that too. So it's a graphic mechanism, I guess. So you're on the concentric circle 2, and you're at angle pi. Well, if this is 0, pi would be 180 away. You know, pi, 180. Okay, so there's your point in r theta in polar coordinates, 2 pi. But look at where you are. You're at x equal minus 2, y is equal to 0. Well, your trig functions told you that, but just looking at it tells you that. On the next one, this one, root 3 times root 3 pi 6 in polar coordinates. Root 3 is something, I'm trying to remember, maybe about 1.7 or something like that. Let me see if I can punch it in quickly and see. I can't do anything very quickly. Okay, because this has square roots, I'm going to turn my phone sideways to give it a scientific calculator type mode. So I'm going to do a 3 and then take a square root of that. Well, 1.732 or something like that. It's irrational number, so it goes on forever. So that's where you go up to about 1.7. That would be somewhere here, and go an angle of 30 degrees, pi 6, whatever you want to call it. That's as far up as you go. There's the point, root 3, 6. Where are you rectangular ways? Your 3/2 this way and square root of 3 over 2 this way. Okay. Again, square root of 3 is about 1.7, and divide that by 2. So you see you're not I was trying to think if there's some other point I could make there. I can't think of any that come to mind. That seemed like I had something, but I've forgotten it now. Okay, let me see if I can loosen my head a little bit more. This morning was quite cool outside. The house got quite cool, and then my first part of lunch, right before this class, it was 80 degrees outside and in the 60s inside. The dog and I went outside for me to finish my lunch, and well, what part of the lunch I got to eat. So it was so nice out there, I didn't want to come back in, but I had to. All right, think we beat that in the ground. So let's move on. They're skipping example 2. They're going on into polar graphs. Let's us do example 2 because We have only done polar to rectangular. We need to do rectangular to polar. Okay, so example 2 will be that. Let's move to our whiteboard. Sorry about that. I'm having trouble breathing. Oh man. Okay. I'm going to clear the drawings here. Does anyone need this any longer? All right. Now, they don't need to tell us this, but they did. Here's the rectangular point. Where is my pen? There it is. Okay. Negative 1, 1. Okay. Now, where are we, Waldo? You go to the left, 1, up 1. So they mentioned in the book you're in the second quadrant. Sure enough, you are. What would be the polar coordinates that correspond to that? Okay. The easiest to do first is your R. Where is my, there it is. Okay. And here's what we do. R squared is equal to x squared plus y squared. Okay. This won't tell you exactly, but it'll get you close. That would be negative 1 squared would be 1, plus 1 squared would be another 1, so that's equal to 2. And if r squared is equal to 2, that implies that r is equal to the square root of 2. Now, it's usually easier to keep r positive. I see no reason to make that a minus 2. I mean minus the square root of 2. Okay, so leave it at that. Okay, remember there's an infinite number of polar coordinates for every point. So let's just pick the easy one. We'll use r is equal to root 2. Okay, the second of those was that tangent of theta, this should be fairly easy to remember, is opposite over adjacent, y over x. And there you just have your values here. Well, this is 1 over a negative 1, which is going to be negative 1. Okay? Well, what is the angle theta that you use to get tangent theta equal to negative 1? Remember, now here's where we have some problems. And you can think of it this way. Theta is equal to the inverse tangent of a negative 1. But remember, inverse tangent only has a range. That's what I was trying to say before, and I said domain. Only has a range of minus pi to pi. Okay? Well, that would be minus pi fourths. Okay. What's wrong with this picture? Remember we said in rectangular coordinates, this is minus 1, 1. Here you are right here. Minus pi fourths would be down here. Okay? So, you could either say this is minus root 2 minus pi fourths. That's a bit awkward. Okay? Or you could say it's root 2. That's the r coordinate. Okay? And then say, well, minus pi fourths is here. This point is obvious up there, so just add pi to it. So this will be minus pi fourths plus pi. That would be 3 pi over 4. So this is the other issue with polar coordinates. Your inverse tangent only gives you a range from negative pi halves to pi halves. That's all, folks. So anything on the quadrants 2 and 3, you're going to have to add pi add pi to it to get your theta. Okay, so you do have to know where you are in your rectangular coordinates, which is pretty easy to do. You just look at it and know where you are. Okay, and then you have to adjust your polar coordinates so you're in that same location. So both of these would give you that same point. Let's see what the book got. Because you're in the second quadrant, that has to be 3/4 pi. That's where you are in the second quadrant. So we got that part right. And then your r is the square root of 2. So that certainly gave you that. Now that's the A part of example 2. Let's do the B part. What if you have a point xy of 0, 2? So I should have written that here because, yuck, this was your xy. Because with just having -1, 1, you don't know whether you're talking about polar or rectangular. Okay, so this time I'll write it xy is equal to, and what was that, 2, 0? No, 0, 2. Now, you could go through the math of it and get it, and that is the way I'm going to do it. But you can look at that and know, where are you? You're 0 on x, positive 2 on y, you're up on the y-axis. Right there, you know you're at pi halves is your theta, and you know your r is equal to 2 there. So you know that this answer before you do a single calculation. Okay, I'm going to write it down. The r theta, and I should have written that here. This is the r theta that corresponds to this xy. Okay, now let's do the r theta here. I already know what it is, but let's do it here. R squared is equal to x squared plus y squared, which would be 0 squared plus 4. Goodness gracious. Yeah, plus 4. Didn't write well. So that would be 4. So your r is equal to 2, which is exactly what we said. This implies r is equal to 2. It could be plus or minus 2, but 0, 2, that's just going to be 2. Okay? And then your theta, I'm just going to jump right to the chase here. Theta is equal to inverse tangent of, SpaghettiOs, y over x, 2 over 0. Can't do it, folks. Can't divide by 0. So in this case, you know you have to be on those only places where x is 0 is on your vertical axis. So therefore you know you have to be pi halves. And pi halves is undefined. Tangent of pi halves is undefined. So this produces pi halves. Okay. So your r theta I can't get my pen to write. There it goes. R theta, and that should be a little r. I don't know why I wrote a capital R there. Is equal to 2 pi halves. There we go. I finally got the pi to write. Okay. Okay. I'm going to have to take just a more of my head is really closing. More of that. Let me see if water will help. I don't know. The other issue is I crammed down lunch as fast as I could, and that's probably not helping the breathing any either. So example 2b, 2 pi halves. Okay, and you really didn't need your equations for that one. You just know it's lying right there. All right, let's move back to, if I can keep breathing here, back to the slideshow. Okay, and current slide. Okay. Now, we're ready now. I'm so sorry. To talk about polar graphs. Okay. Oh boy, they jump right into example 3, not talking about it at all. It says, describe the graph of each polar equation. Confirm each description by converting to a rectangular equation. Okay, so let's just first talk about it. Where is r equal to? R is equal to anywhere on that circle 2 units out from the pole. There's where r is equal to 2. So basically what you have is a circle centered of radius 2 centered at the origin. That's why they call it r, radius 2. That's it. Now you should already know what the rectangular equation for that is, but let's see if we can do it. Okay, so let me get my pen back and my pad back. And what do we know r is? Well, we know that r squared would be 4, 2 squared, which would be 4, and that would be r squared is x squared plus y squared. That's r squared is equal to 4, and that sure enough is the equation of a circle centered at the origin. So there it is. What we knew was going to be the case, that's what it is. Now, theta equal pi thirds. That is a line that goes from the origin up at an angle of pi thirds and keeps going indefinitely. Okay? And in fact, could go infinitely in the opposite direction for any negative r. Okay? So that's going to be a straight line through the origin at an angle of pi thirds. Okay? Well, we know that, if I can, oh, there it is. Your x coordinate here is equal to usually r times the cosine of theta. We just don't have an r given here. So for any r, and let's try just this cosine of pi thirds, that would be, we're going to take r equal 1, basically is what we're doing. That would be cosine of pi thirds is 1/2. Okay, so your x is 1/2. Your y is equal, let's just take 1 again as your r. Sine of pi thirds. Well, I can't see where there. Okay. Okay, I'm having trouble breathing. Sine of pi thirds is root 3 over 2. Okay. Now, that is just one point. when r is equal to 1. You can do any other ones that you want to, but what do you have with that? In fact, let's just do the origin, which would be 0, 0. So this means that your m, your slope here, is going to be root 3 over 2 over 1/2, which is root 3. And your y-intercept, you know, is going to be the origin. So basically this is saying y is equal to root 3x. Okay? And that would be the straight line that has a slope of root 3. Okay? And any value for x. Now, that was a little weirder, but this one is rather strange. Okay? Here's what I would suggest doing first. Say this is secant is 1 over cosine theta. Okay? So that would be r times cosine theta, 1 over r cosine theta. Okay. So what I'm going to do is multiply both sides of the equation. I'm sorry. That's just equal to 1 over cosine theta, sorry. Multiply both sides of the equation by cosine theta, and you get r cosine theta is equal to 1. Well, r cosine theta is r cosine theta. Well, let's just take when theta is equal to r cosine theta is equal to x. So this is the line x equal 1. And that would be, okay, so that's your origin. Line x equal 1 would be the vertical line x equal 1. And I was starting to say, see how the book did. Let's look how the book did, because they have them on here. The first one is simply the circle where r is equal to 2. If you graph it first, you see that it's that circle. And what is that circle in rectangular coordinates? X squared plus y squared is equal to 4. Okay? So that would be your equation in rectangular coordinates, because r is equal to square root of x squared plus y squared. So square both sides, r squared is equal to 4, and that would be x squared plus y squared is equal to 4. Okay. Whoa, hit the wrong key. Okay. So you can confirm this by using the relationship r squared is equal to x squared plus y squared. Obtain the equation x squared plus y squared is equal to 2 squared, which is 4. There's your rectangular equation. Now the next one, the graph of that is just everywhere along the line where your angle theta is equal to pi thirds. Okay, like it may have been a little short here, but I guess they're okay. Okay, everywhere up and down along that, where r is negative here or positive here, if your angle theta was pi thirds, that's the line you get there. And you can do like we did. You can confirm this by using the relationship. Were they saying graph these things? Oh, that's all they were saying. I thought they were saying write them in. Yeah, it does say both. Okay, graph them and write them. So if you do the relationship tan theta is equal to y over x, and take the inverse tangent of that, inverse tangent, or theta then would be the inverse tangent of pi thirds, inverse pi thirds is equal to the inverse tangent of pi thirds of, I'm sorry, y over x, the tangent of theta, tangent of pi thirds, is equal to root 3. And so just plug that in here. Y is equal to, or root 3 is equal to y over x. Oh, I mean 1 over, yuck. All right. Take the tangent of both sides of this. That gives you tangent theta is equal to tangent of pi thirds. And tangent of pi thirds is sine of pi thirds over cosine of pi thirds, which is root 3 over 1. So that's your root 3. And that's, so this is root 3 is equal to y over x. So multiply both sides by x and you get y is equal to root 3x. So there's your equation, and that's exactly what you've got here. So many ways you can go about doing it. Sometimes feel like you're running in circle. This one, the graph of the polar coordinate equation y is equal to secant theta, is not evident by simple inspection, so begin by converting that to a rectangular form using relationship r times the cosine of theta is equal to x. That's always true. That's your conversion there. And r is equal to secant theta. Secant theta is 1 over cosine theta. So multiply both sides by cosine theta, and you get r cosine theta is equal to 1. That's the vertical line. X equal 1. Okay. Now, and there's the graph of it. So this one they converted first and then drew the graph. The others they drew the graph first and then showed that that was a conversion. All right, from the rectangular equation you can see that's the line is a vertical line. R is equal to secant theta. Okay. Now, they've jumped to something else now. This is the technology part at the bottom of page 721. Here's a graph of r is equal to 1/2 theta. Now, that's a rather strange expression there. Coming from a physics viewpoint, theta is an angle, okay? Just a real number, no units. R is a dimension quantity, okay? Even though you may not know what dimension it is, it's some sort of numerical value of something, okay? And so the 1/2 has to have the value, the units, you might say, what you're talking about, to make that true, because otherwise sort of apples and oranges. So length is equal to an angle or half an angle. That's a rather bizarre, okay? And what you do here is you pick you a theta. And usually I start with theta equals 0. And 1/2 of 0, of course, is 0. And so r is equal to 0. So you start right here in the center, okay? R is equal to 0, okay? That's the point right there. And then let theta go to, I mean, you could choose anything. So it's something we know. Theta equal pi 6, say. Okay? We know pi 6 is that 30-degree angle there. Well, if you do pi 6, you'll find out that's something a little bit greater than 1/2. Okay, so then the r is something a little bit greater than 1/2. So at this thing here, this has gone up to something. Now remember, they're showing these as angles as 9. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so you've gone doesn't look like theirs is quite, doesn't look like it's anywhere close to 1/2, and it should be further out than what it appears here. They've drawn this a little too narrow, it looks like to me. Okay, but then you go to pi fourths, that would be something like 3/4. Oh, okay, I'm sorry, I said it wrong. If theta was pi 6, that would be about 1/2, and then half of that is 1/4. So that does look better. That's about 1/4 out here. And then when you say pi is equal to pi fourths, or theta is equal to pi fourths, that's on your diagonal here, then you would be 3/4, half of 3/4 is 3/8. Okay, so you're staying pretty tight. When you get up to theta equal pi, then half of pi would be 1.5. No, I'm sorry, I should have said pi halves. Theta equal pi halves. Half of pi halves would be pi quarters, which would be about 3/4. So this crosses here about 3/4, and that looks about right. And then as you keep going and theta gets bigger, you're going down until, if you let theta go why not, let's just jump on up to pi, and then half of pi would be about 1.5, and sure enough, at theta equal pi, you're over here at about 1.5, a little more than 1.5. And then when you let theta go up to pi, I'm sorry, 3/4 pi, 3/2 pi, that would put you down here, and at 3/2 pi times 1/2 would be 3/4 pi. That would be 4/3. That's about, I don't think I did that right. If theta is 3/2 pi, that puts you down there. Half of 3/2 pi is 3/4 pi. Oh, 3/4 pi. Okay, I said it right and wasn't thinking right. That's 9/4, which would be something a little over 9/4, which would be 2. I'm gonna have to write them out. Goodness gracious, my head's not working well today. If you let theta equal 3 pi over 2, then half of that would be your r, and that would be 3 pi over 4. 3 times that, so 9/4 is 2.25, and that sure enough is what you got here. I was changing it back to 2.5. Okay, and then when you go over here to theta is equal to 2 pi, half of 2 pi is pi, so this would be 3.14. So sure enough, you're there. Well, keep going. Theta equal to 5/2 pi. Okay, theta equal 5/2 pi. You're back up here again. Half of that would be 5/4 pi. Okay, and that would be something a little bit greater than 15/4, and that would be 3 3/4 approximately. Well, that would be, if it's a little bit greater than that, you're almost to 4. And sure enough, if I could get my thing to show up, where in the world is my pen? There it is. Okay, you're almost up to 4 here. Okay, that would be 5/4 pi. Then let's go on around to 3 pi. That would be the next one. So 3 pi over 2 is 3/2 pi. That would be 9/2. That would be 4.5. A little bit greater than that. 1, 2, 3, 4.5, something about like that. So this is making sense. Keep on going a little further, and you see it gets further out here and further out here. It keeps on getting bigger and bigger and bigger. Okay? If you had gone negative here, and rather than doing all the little ones in there, let's first go negative theta is equal to negative pi halves, then r would be negative pi fourths, so that would be negative 3/4, but r is negative 3/4 at pi halves, so that puts it back up here again. So this leaps around like this when you're going negative, more and more negative, and it goes around in the opposite direction like this. So there is your picture. Okay, that's how you do a polar graph. Now that was really awkward. Okay, but it's not that hard to do in polar coordinates if you pick decent ones to do. But they chose to do it graphically and do an XY, and then you would have had, yuck, R would be, goodness gracious, X is equal to, I don't know why they chose that. Oh yeah, X is R cosine theta. So R is 1/2 theta times cosine theta, and Y is equal to 1/2 theta times sine theta. That's what they plug into the computer. I'm glad the computer's doing it, because that would be a true pain in the neck to try to work out this way. Far easier just plug in the values and go the way we were doing, with the values of theta varying from minus 4 pi to 4 pi, and yeah, that's how you get it. I like just plugging in the original formula and doing it that way. Okay, that curve is of the form r is equal to a theta, which is called the spiral of Archimedes. Okay, and good old Archimedes was doing stuff way before he should have been able to do it, but that's one of his. So there's another potential paper topic. Who in the world was Archimedes? How did he develop this spiral? That would be another paper topic. Who uses this? Does anyone really use it? I don't know if they do or not, but it's a pretty interesting graphic there. Okay, notice they intersect first time up here, next time down there, next time up here, next time down there. Never intersect on the horizontal axis, always on the vertical. Okay, so that was example, well, where was it? Yeah, that was the technology at the bottom of page 721. How are we doing on time? Well, we got a few minutes left. Before we get to slope and tangent lines, it looks like example 4 was left off, so let's go to our whiteboard and see if we can pick up from there. All right, anyone needs this any longer? Okay, I'll clear it. And a good thing about example 4, even though it's not listed on your PowerPoints, it is located at larsoncalculus.com. You can see an interactive version of this type of an example. So here is what it says to sketch. Sketch the graph of R is equal to 2 cosine 3 theta. Okay, well, that's pretty ugly writing, but that's what you got. Now they tend to want to go back to rectangular coordinates and sketch it that way. And that may be the easy way to do. But I don't see any reason not to continue trying to do polar graphs, just like it said. So let's just now my circles are going to be pretty lousy. Let's assume that's circle of radius 1. Here's a circle of radius 2. Here's a circle of radius 3. Here's a circle of radius 4. Oh, these are getting terrible, aren't they? And here we'll try to do one of circle of radius 5. Whoa, got too far out there. Okay, whoops. Somewhere in there. That's not a very pretty circle, is it? Okay, let's pick a theta. How about 0? Theta equals 0, 3 times 0 is 0. Cosine of 0 is 1. So that starts when theta equals 0, you're at circle 2. Maybe I did too big of circles here. There's your first point. Okay? How about theta equal pi thirds? Why not? We might even try pi 6. Theta equal pi 6. You know that's going to be somewhere on this angle right here. Okay? Theta equal pi 6. 3 times pi 6 is pi halves. Cosine of pi halves is 0. Okay? So you go from here and you wind up back at 0. 2 times 0. Yuck! Is 0. So it went up here and came back here before it got to pi 6. Okay? So that's a pretty narrow little band there. I've actually made it too big. Something like that. Okay? So let's do theta equal pi thirds, because that worked so well last time. At theta equal pi thirds, 3 times pi thirds would be pi. Cosine of pi is minus 1, so r is equal to minus 2. Well, minus 2, okay, theta equal pi thirds would be this way. A minus 2 would put it down this way. So that would be somewhere right around there. Okay, so it goes from there to that position. I'm not going to quite draw, well, I'll try drawing it. I may not be right yet. So let's do the next theta. How about theta equal, we did 1/6 pi, 2/6 pi, 3/6 pi. That would be pi halves. So if theta is equal to pi halves, 3 times pi halves is 3 halves pi. Cosine of 3 halves pi, it starts at, it goes to 0 again. So this heads back in, if I could find, there's my thing. It goes back in to 0 there. Okay, I think I see what's coming. Let's do theta equal to okay, I need to do a t-table. Okay, theta and r, rather than try and do it in my head. Okay, we did pi 6, pi thirds. This thing is so awkward. Okay, this one we got, oh, we did 0 first. 0 first gave us a 2. Pi 6 gave us a 0. Pi third gave us a -2. Next would be pi. Did we do pi? I thought we did. Yeah, pi gave us a 0 again, I think, wasn't it? 162636. Oh, this was pi halves. That gave us a 0. Okay. And then that's 1/6 pi, 2/6 pi, 3/6 pi, 4/6 pi. That's 2/3 pi. 2 pi over 3. Okay. 3 times that would be 2 pi. Cosine of 2 pi is 1. We're back to 2 again. Okay. So theta equal 3/2 pi, 2/3 pi. That would be up here, and we're back to 2 again. Yuck! This thing is such a pain in the neck. Right there. Okay. Now my 2's are at different lengths, so we don't cross that. We go back to there, and then we go back to here. And then I almost guarantee you, okay, I did that one. Let's do, that's 1/6 pi, 2/6 pi, 3/6 pi, 4/6 pi, 5/6 pi. Okay, 3 times 5/6 pi would be 5/2 pi. Cosine of 5/2 pi is 0. So that's how we got back there. Okay, well, this is too fat of a circle, but we'll live with that now. So that got us back to 0. Okay, 6x pi is just pi. 3 times pi is 3 pi. Cosine of 3 pi is -1 times 2 is -2. So that gets us back to here again. Oops, here. And then it repeats itself. So what we have is a 3-petaled flower, okay? And those are not very pretty, but that's what we've got, okay? If you look in the book, you'll see that's how it does it as well. Now, and that is called a rose curve. It's a 3-petaled rose, okay? And that's, we've just gone over 2 minutes, okay? Sorry about that. It says at the bottom of the page, use a graphing utility to experiment with other rose curves. Note that the rose curves are of the form, we'll do that next time. Let's start with that next time, because I think we need to write that out just so you'll be familiar with that. Okay, sorry. Ran out of time. Let me get my paper in place. And let's see. Homework exercises here would be, think you can do any on this, starting on page 726, starting any of the odds 5 through 13. They're all at Calc Chat. 7's at Calc View. 15 to 23, they're all at Calc Chat. 17's at Calc View. 25 to 33, they're all at Calc Chat. 31's at Calc View. And 35 to 43, they're all at Calc Chat. 37's at Calc View. I think you can do any of the odds 45 to 53, they're all at Calc Chat. 55's at Calc Chat. Let's see, we're going to slope and tangent lines. Okay. 55 or 57 should be at Calc Chat. Try to do 59 and 61. We haven't done something like that in the book, but I don't see anything like it in the book. So they're both at Calc Chat as well. We'll stop there and pick up next time with 63. Any questions? All right. Then if there are no questions, if I can find my cursor anywhere here, then I'm going to stop the sharing. And any final thoughts before we leave? If not, please keep working on your first test, because we will finish 10-4 probably on Monday. Okay, we'll finish it next week. I'll try to have your your test ready for you next week. Okay, be working on your research papers, and we will see you on Monday. Any questions? I'll see most of you later or two of you later this afternoon. Maybe the third one will show up. Okay, and then I'll see the same two of you tomorrow, if he'll show up. Take care. See you either later today, tomorrow, or Monday. Bye-bye. I'm trying to end the session for all of us. There we go. So take care, folks. Bye.